Hi all, welcome to part 4 module 2 logic system design. So recollect what we were discussing in the last class. It is about we just given a definition for so called Boolean algebra, and we saw how it is different from an ordinary algebra that is used in mathematics. Now we will see a very special case of Boolean algebra, that is switching algebra or simply binary logic. So switching algebra is, hope you remember, is the one that is being proposed by Claude Shannon based on what is being proposed by George Boolean in 1854. The switching algebra has been introduced in 1938, right? So after some 100 years. So this is something that is having direct application with the so-called digital circuit. Oh, okay. Now what is a switching algebra? So it is nothing but a special case of Boolean algebra. We can call it as a two-valued Boolean algebra. And hope you remember how Boolean algebra is represented, right? Boolean algebra is an algebraic structure having a set B of some set of elements. Okay, so that is not even George Boole is not clearly defining what is this B. He is just saying that some set of elements are needed. And hope you remember the sixth postulate. What was it? There should be at least two elements. That kind of a restriction is there. Then we are having two operations plus and dot, and we don't know what is this plus and dot. I mean, in Boolean algebra it is defined in a general way, but here we have a meaning for all the three. So when it comes to switching algebra, this B is specifically taken as set containing two elements, that is the binary 0 and 1. So here this 0 and 1 are binary 0 and 1, that they are not decimal, they are not some symbol, nothing. Here what they mean is the special binary 0 and 1 representing off and on state of a circuit, right, of a switch. So with the rules of this plus and dot are as per the table. So this is how they are defining the plus operator for any two operand x and y, and this is how they are defining the dot operator. And you can see that as you are already familiar with the proportional logic, you can see that this 0 is nothing but false, 1 is nothing but true, right? And that case you are getting false, 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 true, false, like that. So in three cases you are getting false, and the system is giving you 1 when both the inputs are true, right? Both the inputs are 1. So this is nothing but the AND operation, right? So the dot operation they are defining as AND operation, right? And this plus is nothing but you can see that it is giving you a false only when all the inputs are false. In other case it is giving you a true or 1, right? So this is nothing but your OR operation. So you can see that this switching algebra is a special case of Boolean algebra where, right, where this B is nothing but this set containing the binary 0 and 1, and that plus is nothing but the OR operation, standard OR operation, and dot is nothing but the AND operation. If that is the case, I am getting the very special case of binary, Boolean algebra called the switching algebra. Now you can see one more table where they are defining something called a complement. I think you already know what is a complement of a binary number. From the first module itself it is clear to you. Just in a complement in the sense from the so just like set theory, how to find out the complement. Universal set minus given set will give you the complement of a given set. Like that, here the universal set is something like 1, right? So that is the maximum value we are having. So the complement of 0 is nothing but 1 minus 0, something like that. You are getting it as 1, and complement of 1 is nothing but the universal set is 1. So 1 minus 1 will give you 0. So just to flip the bits, that's all. So that will give you the complement operation. So this is the complement operation. Same thing you know from module 1 of logic system design as well as from proportional logic, right? So all those things are clear to you. So you can see that the rules are exactly same as AND, OR, and this complement is nothing but the NOT operation, right? NOT operation respectively. See, what is happening here is, let me remind you what we seen so far. That is the first we talk about the general, ordinary algebra, right? In ordinary algebra, we discussed operations like anyone remember what are the operations we discussed? There is something called a closure property, and there is something called an associative property, right? Hope you remember all these things. And there is something called commutative property, right? And the existence of identity element, existence of an inverse for each and every element in the set, and about the distributive property. So these things we saw in general for any mathematical algebraic structure, right? Now a special algebra we defined, that is our what called Boolean algebra, right. In Boolean algebra what we seen is, we define the requirements to be. So, we given a structure for this Boolean algebra, say set B with the two operations, some plus and dot. We don't know what is this plus and dot and anything. Then we define this closure property. We have the requirement that both this plus, the set B should be closed under plus as well as dot. Then associativity was not there, hope you remember. Then commutativity was there. Both the operator plus and dot should be commutative, right, commutative. Then identity, existence of identity was also there, right. Then inverse was not there. Instead of inverse we were having something called a complement. Complement and inverse are two different concepts, keep that in mind. So, inverse means element and its inverse should give you the identity element of the same operator, but here in inverse the element plus its in complement, the element plus its complement will give you identity of this dot. Similarly, element dot its complement will give you identity of plus, like that it is happening. So, that is not same as inverse. And distributivity is also needed here. Distributivity, both this first operator plus should be distributive over dot, and dot should be distributive over plus. Okay, so and one more requirement we were having is cardinality of the set B is at least 2, something like this. Now, keeping all these things in mind, we gone to a special case of Boolean algebra, that is our switching algebra. So, that is something we are defining right now in this video lecture. Switching algebra, how we defined? So, this B we taken like the set 0 1, that is a binary 0 and 1, and plus we defined as or we given the meaning of that of the OR operation, and for dot we given the meaning as that of the AND operation, which you are familiar in your proportional logic and all, right. Or at least right now you know, even though somebody is not knowing what is this AND and OR operation, you can remember these are all standard operation and this is how they are working. So, the AND operation is just equivalent to two switches connected in serial, that also we explained in the first part. You can see that the bulb will be giving you light. You can lighten the bulb only when both switches are closed, indicating that the current is passing through both. So, when all the inputs are 1, you are getting a high in the output, the bulb is you are getting light from the bulb. Okay. Similarly, for plus you can see the it corresponds to switches connected in parallel, right. So, when both switches are closed, you are not getting light from the bulb. In all other case, you are getting the bulb is glowing because the current is passing through one of the paths, that you can see. So, this is how these two operations are defined as per switching algebra. They are fixing it like that. Similarly, this is how the complement operation is defined, so that you can remember. So, the same thing you studied in proportional logic also, or if you are not remembering, this is how the table looks like. So, this is just like 1 plus 1 is 2, how it is coming. So, that is the convention we are having, right. We are following based on that concept, the entire arithmetic is happening, right. Same way these things are defined in this way. Now, when it comes to switching algebra, see, this is how we defined. We defined this plus to be equivalent to OR operation and dot to be equivalent to AND operation, and you know how this OR and we know the table. And the table which we saw right now, this is called the truth table, right. You can see this, we have a name for this, truth table. Same term we are using in proportional logic also, where the table will be containing something like a false, 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 like that. And similarly, here it will be false, true, false, in this way. Same table only, but instead of true and false, here we are having. So, this is something listing all possible combinations of the input instances. For example, here I have a two input variable x and y. So, x can assume two values 0 and 1, or true and false, and y can also assume two values 0 and 1. So, how many possibilities are there for x and y together? Two possibility for, for x we have 2 possibility, y we have 2 possibilities, totally 2 into 2. So, there are 2 power 2 possibility, right, 4 possibility, accordingly 4 rows will be there. So, this is how we are defining the truth table, and corresponding to each instance what is the value of the output, how the circuit is behaving, that is the output. So, in general, if I have n variables, say x1, x2 etc xn, and I have an output to say y is some function of this x1 to xn. You can see that this x1 can have a true value, I mean it is something like a 0 0 0 0 0 1, like that. It can go up to 1 1 1 1. In between all other bits will flip, right? So how many such possibilities are there? X1 can assume 2 value, x2 can assume 2 value, etc. xn can also assume 2 values. So 2 into 2 into n times it will be 2 power n. So in truth table you can see all the 2 power n combinations of the input instances and how the output is related to this particular instance. So that is what is shown by the truth table. So as per the truth table, we are defining our switching algebra. Now the question is it a valid Boolean algebra? So we want the switching algebra to be a Boolean algebra, right? So from that only we have this concept. So whether it is capable of holding these 6 conditions, that is the first question. So closure property, you can see that from the table itself. What is closure property? Hope everyone remember, like when I am taking 2 elements from the set. So here the set is 0 and 1. So the possibilities are like a 0 0 0 1. So all the combination you can see in the table. The output should also from the same set. That is our requirement. Output is also 0 and 1. So that is from B only. So by default both the plus and dot is closed, so that is for sure. Now what about the second criteria, that is commutative? That also you can see if you are taking this say something like 1 plus 0, 0 plus 1, both are giving you the same answer 1. Similarly 1 dot 0, 0 dot 1, both are giving the same answer 0, right? So that you can verify from the table. So it is commutative by default. Then what about the identity element, right? So can you tell me what is the identity element for the plus operation? So you can see that any element plus its identity should give you that element. Similarly any element, it can be 0 also, plus its identity should give you that element. Can you tell me which? So this identity is something unique for the entire set. So you can't fix 2 elements here. What we need is a single element satisfying both these conditions. So can you try what is that element? See, you can see that what is this element? This is 0, right? You can simply substitute 0. And you can see that 1 plus 0 is 1, 0 plus 0 is also 1. So I need a common element. But if I am putting 1 here, 1 plus 1 is what? That is 1, fine. But 0 plus 1 is giving you 1. So it can't be 1. So it is only 0. So from that what we can conclude is 0 is this, the binary 0 is the identity of plus operation. Plus operation is nothing but our OR operation. Now similarly tell me what is the identity element of the dot operator. So the requirement is like 1 dot something is giving you 1. Similarly 0 dot something is giving you 0. Right. I just need the same element, but something common I have to fix here. See, if I am putting, I just have 2 choices, either I can assume 0 or 1, anything will be the answer. If I am putting 0 here, 1 dot 0 will give you 0. So this will be false if I am putting 0. So 0 can't be the identity. So can I try with 1? 1 dot 1 I am getting 1. 0 dot 1 also I am getting 0. Fine. So what you can conclude from these two, you can see that 1 is the identity of this dot operation. So you are getting this also true, right? Dot operation. Sorry, this is dot. Fine. So that about it. Now the third thing and the fourth thing is like the complement operation. So the existence of the complement. I hope you remember how we defined complement. Any element plus its complement should give you the identity of the other operator. Here it is or what is the identity of AND operation, right? Identity of dot. You know identity of dot is 1. So this is my one requirement, and similarly element dot its complement should give you what? The identity of plus. Identity of plus is 0. So this is my requirement. Accordingly, is it true? What we defined is a complement is nothing but simply flip the bit, like if it is 1 the complement is 0, if it is 0 complement is 1, that you know. Then is it true? You can verify 1 plus 1's complement. Complement of 1 is 0. So 1 plus 0 is 1. Similarly 1 dot 0 is also 1. Sorry, 1 dot 1's complement is 0, 1 dot 0 is 0, right? It is true. Similarly for 0, what is the complement? 0 plus complement of 0, that is 1. 0 plus 1 is giving you 1. Similarly 0 dot complement of 0, that is 1, that is also giving you 0. So this is true, right? So accordingly I have a complement concept. I mean, complement is something that is satisfying this requirement, that is also true. Now the last thing is like the distributivity. I just need both distributivity to be true in both direction, that is this take any 3 element x plus y dot z should be equal to, this plus should be distributive over dot means x plus y dot x plus z. So keep this is mind. So here it says that plus is distributive over dot. This is one requirement I am having. Another requirement I am having is x plus y plus z. This dot should be distributive over plus also. This should be equal to x dot y plus x dot z. Can I write like this? This is my criteria, right? Is it true? That also you can verify. So here this is a requirement for distributivity, right? Now this you can verify, see, by using the truth table. You just take x, y, z, and you know for x you can assume 0 and 1, y you can assume 0, 1, z also you can assume 0, 1. So there will be 2 into 2 into 2, 8 rows in the truth table, and corresponding to each of the instance 0, 0, 0, 0, 0, 1, 0, 1, 0, like that for each of the instance. Calculate what is x dot y plus z as well as x dot y plus x dot z, and you can see that both are found to be same. The same thing you can verify for the other formulation also. So one thing it was there in the subsequent slides, that you can see and verify. And what about the last condition? The sixth criteria is like the B should contain at least 2 elements. That is true. It is containing exactly 2. So at least 2 and exactly 2 both are same now. I mean that criteria is satisfied. So this is what is explained in this subsequent slides. Same thing, all the 6 postulates we are trying to see whether the switching algebra, we are saying that it is special case of Boolean algebra. Is it true? Whether it is satisfying all the requirement for Boolean algebra, and that is being verified in detail. Here you can see the closure property is verified, we already seen, right? And what about the identity element? You can see that 0 is acting as the identity element for plus operation and 1 is acting as the identity element for dot operation, right? Now what about the commutative law? That is also true. From the table you can verify it easily. And distributivity, this is what I was saying. So here it is showing like the dot is distributive over plus. When I am doing x dot y plus z, I can see that it is same as x dot y plus x dot z. I can distribute this dot over plus, right? You can see we are taking all the 8 combinations for x, y, z, and this thing is calculated, and this also calculated. You can see that the truth table, these entries are look exactly same, right? Here what I am getting for the same set of instances, I am getting the same thing here also. See, same way you can verify the other one, that is here it is verified that dot is distributive over plus. You can similarly verify that the plus is distributive over dot, like x plus y dot z is x plus y plus x plus z. That you can try as homework. Same way you can try using the truth table method. There is easy way also for doing it, that we will see maybe in the subsequent session, simplification and all. So right now you have to be comfortable with the truth table, that is our requirement. So hope it is clear. Now I think few more things. The last thing is the requirement of complement, that also we verified, like x plus x dash is supposed to give you the identity of dot, that is plus, and similarly x dot is supposed to give you the identity of plus 0. So is it correct? That we are verifying with the value, it is correct. And now the last postulate 6, that is there should be at least 2 element. You can see that it is a 2 valued Boolean algebra, so it is containing exactly 2. So the last requirement is also true. Okay, that's all. Thanks for watching. You can see more about this subject in the subsequent videos. Yes, any doubt you can ask in the classroom also.